So yesterday we talked about slice plots as sort of our first first look at what I think of as the high-level interfaces to the plotting mechanisms. Madikin showed us really neat ways to do this all on the data set level when she was playing with regions and then make plots from that. But the these high-level interfaces basically give us a lot of control in a rather easy package and do a lot for us behind the scenes. Projection plot and slice plot share a lot in common. In fact, in YT, they both derive from the same container class. So the Python inherits from this plot window class. And so a lot of the methods that we saw yesterday, like zoom and the annotations that we looked at, those were actually features of that base class, that plot window class. And so we have access to those same methods for projection plots. Some things may make less sense for a projection, and actually I might have a few questions about that at the end for some of the more experts than with the slice, because of the different way the data is realized. But you basically have access, so everything that we learned yesterday carries over to projection plots today. Yesterday, we did what we called axis-aligned slice plots. That's where the normal to what we were plotting was one of the 3 coordinate axes. Today, we'll look at off-axis plots. And we'll look at them for projection plots, but it'll apply just as well to slice plots. And then we want to learn how to change their style. And my dog is adjusting. Okay. All right. So I'm gonna, whoops, I'm gonna reset my cursor. As I mentioned, this notebook, 04-projectionplots.ipy notebook, is in the Git repo. So if you do a poll, it's only in the Git repo as of this morning. If you do a poll later this afternoon, you'll get it. We're gonna use, I should clear the output, hang on. Just to start clean, I want to start with a clear kernel. We're going to use the isolated galaxy again. Load sample basically just loads the data if it already exists in the cache directory on your computer. The first time you run it, as we saw yesterday, it'll actually download the data set, but now it found it already is living in my .cache and just happily loads it. And so we'll just dive into making a first plot. And this interface looks remarkably similar to the slice plot interface. You give it a data set, you give it a direction that for the slice plot, it was the direction that you want to slice perpendicular to. Here, it's the perpendicular direction for the projection, so the normal direction. And you give it a field. And when I do that, first time through, it has to read things in, read the data, as Matt talked to us about yesterday. I think he called it reluctant loading. So it reluctantly loaded the stuff, and here's our projection. Notice a few things. It's got that same origin-centered stuff that always confuses me, but that same origin equals native will clear that up for you. But notice now the units. Density should be grams per cubic centimeter. In the projection, we lost one of the centimeters. And we'll talk about why in just a moment, but the idea of the projection is instead of just an instantaneous slice through the data set, we're actually integrating out one of the dimensions. And so by integrating out one of the dimensions, we've lost a unit of length. Just to compare to the slice plot, so here's the analogous slice plot. And you notice the units are, as you would expect, grams per cubic centimeter. You notice there's a lot more fine scale structure in the slice plot. Recall by default, the slice plot is going to slice through the center of the domain. So this is looking right through the heart of the galaxy. I did it normal to Z, just as the projection, but in the projection, you see a lot of the finer detail kind of got lost, but you can sort of see more, I don't know if I want to call it, it's more intense towards the center, because you're sort of looking through more material the closer that you get through the center. So these two have very different use cases for you. And in some sense, a projection might be more in line with what you think about as an observation, because you're seeing the integrated light through an object. I think I said both of these, the units on the color scale are different, representing that one is a slice and the other is actually an integral. And so it makes sense just to talk about what yT actually does, what it means by a projection plot. And there's actually a couple of different projections, and I only am going to focus on two of them here. Both of these are integrals. And the first, what we did in that first example, is an example of an unweighted projection. And that's the default. When you just call projection plot, it's going to do this unweighted projection. And in our case, we did a projection along the Z direction. And if you imagine you have some data, so my density, which I'm writing as f of x, y, and z. So at every x, y, and z location in the domain, I've got a density. The projection is just the integral of the density along dz. And so you integrate from the minimum z to the maximum z, and we'll see in a moment you can change that. And you get something that is lower dimensional. So we went from 3 dimensions to 2 dimensions. We lost the z direction. That's what you have to do when you visualize something, right? You're producing a 2D representation of the 3D data set. But you can nicely see that what we saw on the screen, which now I'm representing as capital F here, is just a function of x and y, the orthogonal directions, the directions perpendicular to our normal, and we've integrated out that z direction. And I think I just said all that. In an arbitrary direction, you'd specify some normal. It would dot that into the length element. It would do that integral, and it would still give you something 2-dimensional, but now the coordinates, which I wrote as Q1 and Q2 here, these are the 2 coordinate directions that are perpendicular to our unit normal n hat. Notice that when I do this, I lose a length because I'm basically multiplying f times the length dl or dx. And so the units of the final projection are whatever the units of f were times length. And that was reflected in my projection plot here. I lost 1 unit of length. The alternative, or one of the alternatives, and perhaps one of the more common ones, is to do a weighted projection. In a weighted projection, we introduce another field, and this could be any one of the fields in your data set. And we're going to call that second field the weight. And the integral that we do, and I think I broke this up as I did before. I think it's easier to understand if we first do it in one particular direction and then generalize it. So along the z direction, a weighted projection is just, again, that integral of my function, so density, for instance, as a function of x, y, and z, times whatever that other field is, my weight field, which is also a function of x, y, and z, integrated by along the z direction. And it's normalized. It's normalized by the integral of just the weight in that same direction. Because it's normalized, the resulting projection, so again, this turns a 3-dimensional data set into a 2-dimensional data set. Because it's normalized, that resulting projection has the same units as our field f, lowercase f, because the dz's cancel out here, as you can see in this representation. And the general form, which yT can calculate for you, is f and w, the weight, are both functions of the position. You pick some normal, it integrates along the normal dot dx, and it divides by the integral of the weight along the direction of n hat dot dx as well. So, so why would you use a weighted projection? Well, say for instance, you want to see how the temperature varies, but you really only care about what the temperature is doing where there's mass. You might want to weight your integral by the density so that you get something where where it contributes more to that integral if there's more material there. And so that seems like a reasonable thing to do. In general, also for if you work on like turbulence stuff and you do like Favre averages, which are density weighted averages, this projection does that for you as well if you set the weight field to density. So here's how we do a weighted projection. Same interface, projection plot, same first three arguments. The data set, the orthogonal direction, I'm still doing an axis aligned projection at the moment. The field that I'm going to project, and so in this case, I'm going to project density, temperature, but I'm going to weight it by density. So in this integral here, F is temperature. My result is going to have units of temperature, but in the integrals, I'm going to weight it by the density. And so in the bottom, it's going to be normalized basically by the column density along the line of sight. And I'm going to zoom because, well, one, because it looks better, and two, because it demonstrates that those same methods that we saw yesterday with the slice plot apply equally well to the projection plot, because these are methods that operate on the container, the window that holds the results. And so the zoom works just fine, exactly the same way as it worked with the slice plot. And so here is a density weighted temperature map. Units are Kelvin because it is when you have a weighted projection, you get back something with the same units as the field you're projecting. And you can see sort of hot stuff towards the core. You can sort of see, maybe now you can start to see the structure of this galaxy. Again, I'm not a galaxy person, but I'm trusting the data set name. Oh, I just ran it again. Okay, so that's that. What does the unweighted projection look like? So here's just what the unweighted temperature projection looks like along Z. And you can see it looks nothing like the other one. There's some hot spot here. I don't know what's going on there. Here's the center of the galaxy, and there's a lot of nothingness. And I don't know. This looks more useful to me in terms of understanding what's happening in the data, because out on the edges of this galaxy, there's so little mass that even if it's hot, it's probably not doing much. So weighting it by density enforces that idea that we really care about where there's a lot of mass. This one, unweighted, we see this feature, which is probably really low density, probably not doing much, but for whatever reason is really hot. Here's the corresponding slice plot. Remember, the slice plot is simply just cutting through the domain. There's no integration done. It's just whatever cell centers fall in that slice, or I guess are closest to that slice, are the ones that that are visualized. And you see something that looks kind of in between the two. And if I look at this temperature field, again, the hotspot sort of dominates. It's probably, you know, if this is your simulation, you probably get value from all three of these visualizations. But in terms of understanding the dynamics of what's happening, the density weighted slice plot probably is more closely aligned with your intuition in understanding where the temperature is based on where the material is, where the mass is. So that's sort of one of the main use cases for projection plots. And the weighted projection plot is often quite a useful thing, especially when dealing with stuff like temperature or velocity, or if you want to look at turbulence and you really want to see the effects only where there's a lot of mass, where perhaps it can have the most impact. Madikin yesterday talked about regions, and I don't think when we did the slices yesterday, we applied any of them to regions, but now we'll look to see that you can do these same projections on a region, and they work the same. It just allows you to extract a subset of the data set and then do the projection on that. And again, all of this applies equally well to slice plots as well. You can do regions on slice plots, but I'll stick with projections for now. So we're going to limit ourselves to a narrow region. And the idea is that we're going to pick basically a rectangular domain, a rectangular prism, that in the X and Y directions is the full extent of the domain, but in the Z direction, it's rather narrow, and it's centered on the center of the galaxy. And you can imagine the limit that I make that slice really, really thin, the projection is going to start to look like the slice because there's just not that much material to integrate through. So I'm going to build a region by specifying a lower left and an upper right value. So the coordinates of my rectangular prism. So I need an X, Y, and Z coordinate of the lower left and an X, Y, and Z coordinate of the upper right corner of my prism. I'm going to access the data set information. So where the center is for my domain, where the left edge is, and where the right edge is. I'm going to set the depth of my my slice to be 40 kiloparsecs, which look up on here. This is 10 kiloparsecs. So maybe the whole galaxy across is on the order of 10 to 20 kiloparsecs across. So this will easily encompass my whole galaxy, or at least, I don't know, the guts of the galaxy, if that's a galactic astronomy term. And then I'm going to just keep my lower left and upper right to be the domain boundaries, but in the Z direction for X and Y, but in the Z direction, and remember we count from 0. So 0 is X, 1 is Y, 2 is Z. I'm going to make it the center in Z minus half of my depth. And the upper right corner in the Z direction is going to be basically the lower left plus the full depth. Or all, identically, I could have done center plus half the depth. So this is a slab that in the Z direction has a thickness of depth. And then I'm going to create a region that's a box. And a box region just takes a lower left and an upper right. And hopefully it works. I always like to print things. So here I'm printing my region, and it's showing me the extent of my region. Here's the center. That's the center of my domain. The lower left edge is 0 and 0. That's the left edge of the whole domain for the simulation. But in the Z, it's, I don't know what that is. That's something, a number of megaparsecs. And the right edge you can see is the full domain, but then just a little bit greater than that in the Z direction. So it looks like I've made my slab that is the full domain extent in X and Y, but narrow in the Z direction. And I can create my, oh, look at that. I made a slice. Why did I make a slice? Huh. Well, let's play with this. I have to change the notebook in the Git. Here's a slice plot of that region. You pass in, this is my OCD here. You pass in the data set, the normal direction, the density. I always like to fix up the coordinates. And now you tell it to do the operation on the region that I just created by using the keyword argument data source. That's a slice. I actually meant to do a projection, but I think I was playing around with things and probably why this changed. So here's my projection. And you can see in the projection that there is a lot more structure now. or you can see more structure now than we saw in the original projection. I scrolled up so fast, so much that we've probably lost the mental image. But just sort of focus on here where the fine scale structure seems to be smoothed out, because now I'm integrating through the whole domain. And if I look at what I just created, it looks like I have a little bit more structure there. And I can make my, my domain even smaller, the depth even smaller. So I'm going to remake my region, and I'm going to remake my projection plot. And when I do this, notice what happens. There's a lot of volume in my domain where I didn't get anything. And the reason is, and one of the experts can correct me if I'm wrong, but I've now made my domain so narrow in the Z direction, 20 kiloparsecs, that the zones in these coarse levels of the simulation data, they're actually as big or bigger than that. And so no zone centers fall into my region. And so there was nothing to integrate through. And so that's something to keep in mind when you play with these projections. If you make a region, it's only the data whose centers fall inside of that region that are going to be used in the projection. Hopefully I said that correctly. And I think yes. I thought that was interesting enough that I made it green. There's a comment. No?
Yeah, you got it right. That's perfect.
Excellent. Okay. So anything that I put in green is something that I sort of relearned while I was making these notebooks. And so that's one of those fun things. Because naturally I started out making this slab really, really thin, and I got all this white and I was like, what is going on? And then I realized what's happening. All right. So, and this works. We'll do a spherical region later, and we still have that challenge question for the afternoon to do the Mickey Mouse projection. Put 3 spheres together in a union to look like the Disney logo. So someone can try that for this galaxy. And we won't tell Disney, don't worry. So, so far we've talked about what are called axis-aligned projections. Just like yesterday, we talked about axis-aligned slices. That's where we're doing the slice along, or the projection along, one of the coordinate axes. I hesitate to use the word easy, but that's a simpler operation for YT to do, just in terms of how the data is laid out, because underneath it all, there's some sort of logical structure that's aligned with those axes. If we do an off-axis projection, that's where I'm going to integrate along some arbitrary direction that's not aligned with the coordinate axes. It's got to do something fancier. And in fact, under the hood, what YT does is it leverages the same infrastructure that's used for volume rendering, that Stephanie will talk about this afternoon, to do these off-axis projections. And in short, what it's going to do is you're going to pick some direction, a normal direction, that is based on just a vector. You're going to pass in a vector. And YT is going to shoot rays through the volume parallel to that normal, and it's going to integrate up the data, either weighted or unweighted or whatever you've asked for, along those rays until they hit an image plane, which is what's going to be displayed on your screen. So it's an operation that's going to be very much similar to how the volume rendering is done later. Oh, and just to make things fun, wait, what am I doing here? Yeah, okay. So just to make things fun, I also, why did I create this sphere? I was playing with things so much yesterday that maybe I got lost. So I created a spherical region, but I didn't actually use it as the data source region. So let me just comment this out. This is one of
You
those.
created the sphere to get the angular momentum.
Thank you. Thank you. Someone's paying attention. Very good. Thank you, whoever you are, mystery voice. Right. So in this example, we're going to try and make a projection along the direction of the angular momentum vector. And as my mystery voice told us, just to make it more meaningful, instead of having the whole domain participate, we're going to use some small region. 15 kiloparsecs, if you remember from the scale that we saw in the projections above, is mainly just going to get us the galaxy itself. And so we're going to make a spherical region around the galaxy. We're going to compute the angular momentum. Matt showed us some of the fun quantities we can get when he did his tour of working with data yesterday. One of the quantities we can get is the angular momentum vector. And so we just apply that to our region, and it gives us the angular momentum vector. We print it out here just so we can see what it looks like. And then we do our off-axis projection plot. Give it the data set, give it the direction. Before, we were giving it the direction that is either X, Y, or Z, one of the axis aligned directions. Now we're giving it a direction that is a vector. And so it's going to, same interface, but it's going to know what to do when we pass it some arbitrary vector. I'm still going to work on density. I'm going to tell it use the center to be the center of my sphere. I actually don't need this because the center of the sphere is the center of the domain, which is the default, but it's nice just to see how we can set that. And I'm going to set the width of my projection just to be 50 kiloparsecs. And when I do that, this takes a bit more time. So it's working on it. Here's my angular momentum vector. It doesn't have much meaning to me, except, you know, it's got the right units, so that's good. And here's what my projection looks like. It really looks kind of cool. It's got this little like glowing effect behind it. So this is a smaller domain, a projection in a direction that is not aligned with the axes. It was an unweighted direction, which is reflected by my units here. I lost 1 unit of length. And notice now that the axes, they're not X and Y. They're now X, image X and image Y. This change in the name reflects the idea that this image plane isn't actually aligned with X and Y. It's some image plane that is perpendicular to my normal vector that I supplied. And so this is sort of a fiducial X and Y that were used in the projection to create the image. All right. One other thing, which I won't play with now because this data set, it turns out it didn't make much of a difference for. But if you notice in the info that YT prints out, it tells you that it's making a fixed resolution buffer of density that's 800 by 800. So that's the number of pixels it's using. So in that, in computing that projection, it's going to shoot rays through the domain and have those rays intersect that image plane, where that image plane has a resolution of 800 by 800 pixels. So that's going to sort of set the scale for how fine detail you can see in your data set. If you're making a really high resolution image and have a really high resolution data set, you might want to bump up those numbers. You might want to use a bigger fixed resolution buffer at the expense at the expense of, you know, computational work. It's going to take longer to be done. And I just note here that you can change the size of the buffer using the set buff size option. You can do the same thing with projections that we did with slice plots. Here's another off-axis projection. Just, well, it's not really off-axis. I don't know why I did that. It's actually off-axis aligned on an axis. Oh, no, I'm sorry. This is off-axis. because there's 2 ones, not just 1 1. So this is in some diagonal direction in my domain, and zoomed in by a power of 50. Here you can actually see what looks like a thin disk in this galaxy simulation. Again, as much as I know about galaxies. Again, the units show the same, that this is not aligned, and so instead of just X, it has image X in it. And I've tried to put some links that give us more information on all the fun things you can do with projection plots. All right, I think I'm doing all right with time. 2 more bits to go through. We already saw the example of a region where we used the box, which is basically a rectangular prism. We made it narrow in the Z direction so that we're integrating through a lot less of the domain than the full domain. But you can also do a sphere. If I don't put units on the center, it's code units. And so this is the midpoint, the center of the domain. 20 kiloparsecs in radius creates a sphere. My interface looks, again, the same as we've been doing before. Data set, direction I'm projecting along. So this will be an axis aligned projection. I'm going to project the velocity magnitude. That's a derived variable in this data set. So it's going to compute that from the x velocity and the y velocity as needed. It's going to weight it by density. So this is really going to show me where the kinetic energy is in some sense. The data source is the sphere. So that means it's going to do this projection just in the region that is the sphere. I always like to reset the origin so that the coordinates are in sync with what they are in the actual simulation. And I'm going to make my plot window small. So I'm going to zoom in a bit. Since I only have a 20 kilometer radius sphere, I don't need the whole megaparsec domain. So it did velocity magnitude. It gives me this warning that there's some places where there wasn't data, and you can see those just in the corner here because, well, I'm plotting a sphere in a square domain. There's going to be some places where there's no data. But this looks pretty cool. This is basically where the magnitude of, I guess this is more like momentum. This is where the momentum is really strong in the galaxy. And you can kind of get a sense of, I might be reading too much into this data set, but you can kind of get some sense of some structure in the disk. Okay, final bit is annotations. We talked about annotations a little bit yesterday. We'll dive into them a little bit more today, and I've provided the link for the page that lists all of the many, many annotations that you can do. And we'll talk just a little bit about how YT stores these annotations. So here's one of the docs. All of the annotations.
What are you doing?
I'm sorry?
Where do you have your 20 pages? I want to see the 20 pages now. I'll give you the number. Go. Take this 20 pages.
I'm not sure that's meant for me.
20 problems. Got it? You cannot do so many.
I'm not.
But still you have.
I don't think that's meant for you.
Yeah, I don't think that's meant for me. Someone might want to mute.
Yeah, I don't think I can force a mute.
Yeah.
Let me see. I'm gonna try to get host
Okay.
You study today.
so I can do that.
These 2 days you needed to wipe it. First you have to wipe it.
See.
You needed to study
Let's see if there's someone.
3 days. So now you have to study 2 days. Econ, makes sense?
Yeah, if I can.
Okay.
Yeah, sorry. Maybe we can just. I'm trying to get host from
Yeah.
somebody.
I
so
will
that can
try
do
to
stuff.
carry on.
Yeah, 'cause-
And those of you who are online, if you don't have a question, if you can mute, that would be helpful because we can hear some background noise.
Yeah, we have about 5 people who are unmuted. So if those of you who can mute, please do.
All right. Thank you, everyone. Okay, so annotations. All of the annotation functions that we're going to talk about, they can apply to slice plots or projection plots or other plots, basically anything that uses that same plot window container class as their base. All the methods are going to start with annotate, and it's going to be annotate underscore something. And that something is basically going to be the description of what you want to do. And in the actual code itself, in the yT source code, these are referred to as callbacks, because basically what's going to happen is yT is going to maintain a list of all the annotations you want to do. And then when you make your plot, it's just going to do those calls to those functions to add those annotations to your plot. So we'll take a look at all that. I like to start with something clean. So here's my clean projection. This is the first projection we made up at the start of this tutorial. And now we're going to draw a circle on it. So we're going to draw a circle with a radius of 30 kiloparsecs. So maybe this is highlighting some critical orbital radius in your galaxy. Annotate sphere is what we want for that. Takes a center, takes a radius. I'm giving it the units, and it can take a number of different arguments. I'm just going to say I want the color to be black. And when I do that, I get my circle. And so that's 30 kiloparsecs. And so, you know, this is useful for publications, for instance. If you want to sort of highlight some feature and give some sense of scale, you can draw some circles on there. There's also annotate contour. I'm not going to show that, but you can draw contours of, so this is density that I projected. You can draw contours of some other field on top of this. I can draw a title. It's an isolated galaxy, so I figured it was lonely. So I added a title to my plot, a lonely galaxy. But notice that when I annotate now, I have the previous annotation. So I still have my circle, and now I have my title. So it's applying both of them. So the annotations are additive. It basically, yT is maintaining a list of all the annotations that apply to this plot object P, and it's just adding to that list or appending to that list as we add them. I can add a timestamp. That's a nice thing to do. And so when I add the timestamp, it adds in the bottom left of my domain that this is 442 million. Yeah, it's a lot of years. I'm used to my simulations. If they can get like milliseconds, I'm happy. So this is, you know, this is really impressive as far as I'm concerned. But notice that I still have the circle. I still have the time. Well, I just added the time, and I still have the title. So all of those annotations are maintained. One of the things I realized while working on this is there was no easy way to see the list of annotations. And so that's a nice thing that we can add as a feature later. But if you look inside this plot window object, the list of annotations is just a list. And so I can loop over the list, which is called underscore callbacks. That underscore basically means we shouldn't be playing with it, but you know, they're not going to yell at us. And I see I have 3 callbacks, 0, 1, 2. That's the index in the list. The sphere callback, that's the first I did. The title callback, that's the second one I did. And the timestamp callback, that's the third one that I did. You can remove callbacks. So since they keep adding to it, say I want to get rid of one of them, you can use Annotate Clear to get rid of callbacks. If I just call Annotate Clear with no arguments, it will remove all the callbacks. If I pass in an index, it's going to remove that callback. So if I want to remove the timestamp callback, I can pass in index 2. If I want to remove the title, I can pass in index 1, and so forth. Since this is a list under the hood, if I pass in -1, that refers to the last item. And so if I just want to remove the last callback, I can say Annotate Clear minus 1. That last one will be removed. So I'm going to remove 1, which is a title callback. And you see the title's gone, but the sphere is still there. Wow. So that's basically it. And one of the things that I was going to do this afternoon during our hack time is I was going to make a proper method to list these annotations so that Annotate Clear is a little easier to use if you want to remove a specific one. But to end for the afternoon exercise, here is an example that shows all sorts of annotations that you can add to a plot. So adding arrows, lengths, little call out boxes to them. And so maybe you can play with this and extend this some and play around with adding different annotations, changing them, removing them, changing some of the properties of the annotations where you're going to look at the help, for instance, to understand how things work. And I'm going to end with a question for some more of the experts. And the question I have is, if I do a projection plot where basically I've integrated through the domain and then I annotate the velocity field on it, when it draws those arrows, which we did yesterday with the slice plot, is it using a projected velocity field to draw those? Or how's it getting the velocity information? So maybe
it uses a projected one. So it
Okay.
only really makes sense to do that when you're doing an average. So weighted projections, it might
okay.
make sense.
Yeah. So, okay. Very good. Yeah, I was curious about that. So I didn't show annotating the velocity field or contours or things like that on projection plots because I don't have as intuitive a feel for that. But those, to me, are very useful things to do on slice plots. Thank you, Matt. So that's my show for this morning. If there's any more questions, I'm happy to answer or defer them to more experty people.